All right, let's look at the homework 2.5, problem number 9. All right, so look at this following function, and we want to determine if the discontinuity is removable or not removable. All right, so part A. All right, so you have x to the fourth over minus 1 over x minus 1, and obviously at 1, the function isn't even defined there, so we know that there's a discontinuity there. All right, but is it removable? All right, so what you need to do is that you can just try to take the limit as x approaches 1, right? So 1's right there. So you have x to the fourth minus 1 over x minus 1, right? And obviously, if you plug in 1 for x, the denominator goes to 0, and here the numerator goes to 0. So we're going to have to do something. All right, so luckily, we can factor out the numerator. So let's do that. So this is, let's see. So you can think of x to the fourth as x squared squared. So it's a difference in square. So we can factor it out as x squared minus 1 times x squared plus 1, and all over x minus 1, right? And we're going to go a little bit further. So we want to factor this one out. So I'm going to probably go here. All right, so you have a limit as x approaches 1, and factor this guy out. So you have a difference in square. So you have x minus 1 times quantity x plus 1, and we still have x squared plus 1 as x minus 1, right? So then we can cancel common factor on top and bottom. So you have a quantity x minus 1. We can cancel those out. And then the limit is simply, right, so you can just plug in 1. So it's a 1 plus 1 times 1 squared plus 1. So it's a 2 times 2. So it's 4. Right? So the limit exists. So tendency from both sides is the function value is heading toward 4, but the only problem is that that function is not defined at the x equals 1, because x equals 1 will make the denominator equal to 0. Also make the numerator equal to 0 too. All right, so therefore this one is removable, because we can simply redefine this function at x equals 1 as 4, then the hole will be filled. All right, so this is going to be discontinuity is removable. All right, then the function that is going to be is sitting right here, this function here. So this is going to be the function it's going to look like. So this is going to be our g of x. All right, so let's see. I'm going to put that in there. So this is x plus 1 times x squared plus 1. All right, let's check the answer first. All right, I came back and looks like we got part A correctly. All right, let's do part B. All right, so for part B, we're going to actually do the same thing. The problem seems like, at 9, the denominator is 0. So let's see if limit exists at 9. So you have a limit as x approaches 9. And then you have x cubed minus x squared minus 72x over x minus 9, right? Then I'm going to go ahead and factor this guy out. So you have a limit as x approaches 9, all right? And seems like everyone has x in it, so I'm going to pull out x, right? Then you have a x squared minus x minus 72, right? And I think we can factor even further, so I'm going to do that. So limit as x approaches 9. All right, so x is already there, and I think we can factor this guy out as, and we kind of want the x minus 9, right? Hoping that that's there. So it's going to be x plus 8, right? So then you have x minus 9, right? So you can actually cancel common factor out. So you're left with x times quantity x plus 8. So the limit is going to be, plug in 9 here, 9 times 9 plus 8. I'm going to have to write it down, so I can't do it in my head. So you have 9 times, all right, 9 plus 8, so 17. All right, so what's this? So 7 times 9 is 63, and 9 times 1 is 9, so 153. All right. So the value is there still, limit exists, but the only problem is that there's a missing point at x equals 9. All right, so this one is actually exactly the same as before. The discontinuity is removable at x equals 9, and the function is sitting right here. So this is going to be, maybe I should use a different color. All right, so x times x plus 8 is the function. So let's type it in. All right, let's see. All right, so it is removable, and the function is x times x plus 8. All right, let's check the answer. All right, I came back, and looks like we got part B correctly. All right, so let's do part C. All right, so for part C, the function is greatest integer function of sine of x, right, at x equals pi. All right, so let's take the limit. All right, so in this case, I'm going to have to do a one-sided limit because of this greatest integer function. So here, let's take a limit of this function. All right, sine of x as x approaches pi from the left. And also, we're going to have to do a limit of the same function. All right, and it's going to approach from pi from the right. All right, so let's look at the picture a bit though. So if you look at the sine function, all right, so sine function looks kind of like this. So let's see. So here's a 0, here is pi, and maybe 2 pi. All right, so it's going to look like this. Maybe 1 and then maybe -1. So maybe I'll put a little bit of here. So this is y equals 1, and here is y equals -1. All right. Then sine curve goes like this. Start from 0, go up and down and up. Right? All right. But the problem is that we have to take the floor or the greatest integer. Right? So the function is going to look like this. Okay, so when it's exactly 1, it's going to be 1. Right? But if it's below 1 up to here, it's going to be 0 because of the 0 is the greatest integer less than equal to that. And it wants to go below, so this is slightly negative, so it's going to actually go down to -1. And here, so actually then it's going to stay -1 up to here, and it jumps up here, right? All right, and here, of course, we have 0 here. All right. All right, so you can see it's kind of hard to see, so it's going to be that and jump up here and here, and there's a gap there, right? So at x equals pi, this function has a gap discontinuity, and since the tendency from the left hand side of pi, it's going to be 0. And the tendency from the right-hand side is going to be actually -1, because heading toward -1 here, all right? So therefore, limit it doesn't exist there, so it's not removable, because there's a gap there, so you can't remove it. All right, so let's answer that. So here, discontinuity is not removable, and let's see, so if for function, you just have to put does not exist, right? Yeah, so you're just gonna put does not exist here, right? Does not exist. All right, let's check the answer. All right, it came back, and looks like we got this one correctly as well. All right, that's it. I hope that this was clear.